In this lecture, we will talk about phase 2. In phase 1, the two ike gateways authenticated each other and established a secure channel of communication. And then they're going to move on to the next phase. The next phase is agreeing on what type of encryption is going to be used to encrypt the traffic. This phase is called quick mode. And quick mode occurs after phase 1 is completed. And the two sides would need to negotiate what traffic is going to get encrypted, and what security algorithms are going to be used to encrypt the traffic. This is the Security Association Agreement. In the quick mode exchange, they exchange new nonces. Those nonces are going to be used to generate new shared secret key. And those keys are going to be used to encrypt the traffic. So let's see how this happens. So, first let's talk about phase 2 without PFS. PFS is perfect forward secrecy. We will talk about PFS in a little bit. So, the initiator firewall would send a message with an outbound security parameter index. In this message, it has the source and destination IP addresses that needs to be encrypted. It's going to send the transform sets, which is what encryption list of encryption protocols that it would like to use. And then, it's going to send another new number used once. That's going to get used in the calculation. But it's going to include another piece of information here. This is called hash 1. What hash 1 is? It is a hash of the entire message minus the padding, any padding that's in the message. And then the security association information, which transforms it would like to use, like triple DES, AES, MD5. If it will use perfect forward secrecy, it is going to send PFS information. It is going to send this information, and that's the SA, which is Security Association. And it is going to send also nonce I, which is the nonce for the initiator. Okay, so this is the hash. This hash is used as part of authenticating the message. It's going to encrypt the entire message here. The source, destination, transforms, nonce, hash 1, which is here. And it's going to encrypt it with SKIDE, which is the key that was derived from phase 1. The other side would decrypt. It will validate the hash. It will ensure that the message checks out. It will verify that both sides are using the same keys for authentication. If someone tries to put itself in the middle, it will not be able to. When the message arrives, this was going to be marked as an index with security parameter index as inbound SPI. So, the outbound SPI on one firewall is the inbound SPI of the other firewall. It's going to decrypt and validate the hash. And then, it's going to send a message. This message will have what networks will be encrypted. If it agrees on the network A and network B pair, it's going to respond with network B and network A pair, in the opposite direction. Because traffic going from here, network A, to network B, is going to be the opposite in the opposite direction. This is called the proxy IDs. You are going to see proxy IDs mentioned in many vendors' implementations, sometimes it's referred to as encryption domain. And then, it's going to generate the second hash. The second hash has the hash of the entire message with the SA and the nonce responder. And then it's going to encrypt the entire message with SKIDE, that was derived from phase 1. The message arrives back, so the outbound SPI becomes the inbound SPI. So the network pair that will be encrypted will be the transposed number on the other side. Outbound SPI on this side will be the inbound SPI on the other side. And then what happens is that it is going to validate the message. It will do a message validation which has hash 3. It is using the message and the nonce I and nonce R in this validation. and this message will be sent to the opposite side. In that phase, they exchange this information and validate each other using authentication. What's going to get calculated as new keys for the IPsec phase? The new key is referred to as keymat. The keymat is a pseudo-random function. It uses the skid for the function input and the protocol ESP. It uses the SPI, which is the outbound SPI, as well as the nonce of the initiator and the nonce of the responder. So all those are used in a function to produce the keymat. That keymat is going to be the symmetric key that's going to get used to encrypt traffic going to the other firewall. So this is the outbound SPI key to send traffic from network A to network B on the other side. There's different key on both sides. So this side would use a different set of keys. And the reason why is that the outbound SPI is different. It's using the same formula but different outbound SPI numbers. Now, because the traffic is getting sent with one key, and it's going to get decrypted with that same key. And this firewall knows what that key is since it has all the input information. It has all the parameters of the function, the skid, protocol, SPI and nonce initiator and nonce responder. The traffic encrypted from this side to this side will use a different key than traffic encrypted from the opposite side. So the network destination pair is referred to as proxy IDs. There's a quick mode done for each pair. Each pair of source destination has a quick mode that gets negotiated. There's a security parameter index that gets created on both sides. That security parameter index is going to be used to identify which policy to use. And we're going to cover this process in a future lecture. We will see how does the firewall process the packets for IPsec, and the process repeats for the lifetime, until the security association expires. And you can set that association to have a lifetime, whether it is by time or by kilobyte. From that point onward, they are going to renew the keys when the lifetime expires. In quick mode without PFS, we use the keys that were produced by the phase 1 process. That's why phase 1 was important, because phase 1 created skid, A, E and D. It created the skidd that gets used to create the keying information for phase 2, which is a symmetric key for phase 2 that's going to get used to encrypt and decrypt the traffic on both firewalls. There are three messages: QM1, QM2, and QM3. Now let's talk about perfect forward secrecy. The perfect forward secrecy avoids potential disclosure if the private key was compromised. In that case, you're going to use the Diffie-Hellman key in exchanging phase 2. So each Diffie-Hellman exchange requires larger exponentiation, because we are going to have to create different sets of keys that results in increased CPU. So let's see how that happens. The outbound SPI is created. This side would send a request for network A to network B pair to be encrypted, and what transform set, what is the nonce, and the Diffie-Hellman keys. So, it's going to generate a Diffie-Hellman key pair. That Diffie-Hellman key will be the public key of this firewall. It is going to run the same function. It gets #1, which has as input the skid, A, that was created in phase 1. And it's going to add the entire message without padding and the nonce of the initiator. It's going to put this in the hash function. And then it's going to encrypt with skide. The responder would decrypt and validate the hash. It's going to check the proposal. It's going to create inbound SPI and it's going to respond with its own pair, which should be the opposite of this initial message. And then, it's going to send a Diffie-Hellman public key. That Diffie-Hellman key would be used in generating new keys. And it will send #2, which is pretty much the pseudo-random function run using the skid A. And it's going to use the entire message with the nonce initiator and nonce responder, as well as the security association message. So both nonces are going to get used here. The nonce that was there was sent from the responder, the nonce that was received by the initiator. The message is going to arrive back and it's going to create the inbound SPI. So you have an outbound SPI for network A going to network B, or A-B pair. And then a different outbound SPI for network B to network A pair. Then the last message is validating that everything was received without errors. It's using #3 here. It uses the message as well as nonce I and nonce R and appends 0. So basically this is a concatenation of the message ID, and nonce I, and nonce R. This completes the validation process. Now what happens is, it's going to calculate a Diffie-Hellman shared secret key based on the public key that was sent, and the public key that was received during the quick mode messages. Same process that was done during phase 1 Diffie-Hellman calculation. The other side would calculate a shared secret key, however, it's going to be a different key. So this side key mat is going to be using the Diffie-Hellman shared secret key that's common amongst the two, as well as the SPI, and nonce initiator as well as nonce responder. You will have different keys on each side, one SPI from A to B, and the other SPI from B to A, in the opposite direction. So, having the SPI in the calculation would cause each direction to have a different set of keys. The rest of the formula is the same as the nonce initiator and nonce responder are the same. The process of regenerating the keys happens in the same manner, same like the process without PFS. Every time the lifetime expires, a new set of keys are generated. You are going to have a new Diffie-Hellman key exchange when the lifetime expires. The two sides are going to generate new keys and use those keys in new key mats. A new Diffie-Hellman shared secret key based on the negotiated Diffie-Hellman keys. You will have a new key mat created on each side, every time the lifetime of the security association expires. It's going to process another phase 2 quick mode to reinitiate keys, for encrypting from that point on forward until the lifetime expires. Hopefully you enjoyed this lecture. We will discuss more in the next lecture.